to invite Dan Scolnic to present first talk, LSST DESC recommendations for DDF strategy. Dan, I will let you know 3 minutes before your time. Okay.
Great. Okay,
Please.
so let me share my screen again. Okay, can people see this okay? I'm just gonna.
Yeah, it's okay.
Looks good.
Great. Okay, so thanks for having me. I really appreciate this cross collaboration invitation. And I'll talk today about what DESC, the Dark Energy Science Collaboration, wants for the LSST Deep Drilling Field strategy. And I'll say, kind of before I get too much into it, that I'm also now on the LSST Survey Cadence Optimization Committee, which kind of tries to find a consensus across the collaborations. And I could kind of say that for the deep drilling fields, if DESC and AGN could agree, I think that will become the reality. So I think it's super important that we talk to each other. I'm really appreciative that I could do so, and I'll leave a good amount of time for discussion after my talk, and also be in the discussion later. So this will be recommendations based on from the DESC Observing Strategy Working Group that I co-lead with Michel Lochner, and I'm kind of really emphasize work by Philippe Gris. He's in France, and a lot of the kind of plots of kind of how well different things do are from him. And I just put his email address in case people want to check in with him. Okay, so this is the observing strategy team. So we're a big team, and in DESC we have a number of different probes, and kind of one of the difficulties for observing strategy is trying to find strategies that supernovae or weak lensing or large scale structure like, and that's quite the challenge. But it's a really interesting team. And now our two kind of big sets of papers, our two papers are online, so you can find them. So the links are here. So the first on the left is the Dark Energy Science Collaboration Cadence Note. So this was the kind of direct response with the 7 questions that the SCOC had put out, and kind of really only one-ish of them was about the deep drilling field. So, and we had to our note was about, you know, a lot about the wide, fast, deep also. But in the end of our document, if you look at it, there's kind of a lot of discussion about the deep drilling field. So you have to go kind of all the way to the appendix, and I'll talk about that today, but that is in there. And then we also wrote an entire paper that kind of provided the foundation justification for the Cadence Note. So this is the impact of observing strategy on cosmological constraints with LSST. So I give the archive link below, and in there we detail every single metric, which is now in math. So kind of now be able to be run by the project. And kind of all the assumptions and algorithms that were used to kind of analyze different strategies. So in case it's useful to people here, we have now a lot of things in math, and maybe there's some things that people could use. I'll say though that generally this paper focused on wide, fast, deep, and less as much on DDF, because wide, fast, deep is the bigger battle, but a lot of the metrics can still be used for DDF. Okay. All right, so just quickly, I don't want to spend too much time on this, but we have a number of probes, and one thing that we did, which is, I think, particularly useful for some of the discussions I'd like to have with AGN, is I make plots like this, where we break, so we're showing on the x-axis the fractional change in for some metric, and it could be any metric, over baseline. So metric minus baseline over baseline. And then in the legend, you can see that we have different metrics. So this is just about I-band depth and standard deviation. And then this is then broken into different survey strategies. Because one of the toughest things we found is just trying to visualize who was agreeing between different probes and why and where. And it would be kind of particularly nice, kind of as maybe the discussions between DESC and AGN Advanced, if we could start trying to make some of these plots, like, okay, we both like this or we both don't like this. And the amount of simulations for DDF is not as advanced right now to do this, but I think that's going to happen really soon. So that'd be great. So basically, then what we could start to do is we could make with these kind of what we call consensus plots, where we're saying, all right, here's all these different probes, whether it's weak lensing or supernovae or kilonovae or lens supernovae or photo Z's, and you could see this fractional change of different strategies. So different strategies that the project has made, and kind of how that depends on things. And are there places where everyone agrees? And I think that's the biggest thing that I don't really know yet between DESC and AGN for DDFs. And part of that is just not having enough strategies. But this is the kind of work that I would like to do with the AGN group. These are the kind of plots I like to make. Okay. All right, so now I want to transition to the DDFs, and our Cadence note recommendations can be kind of summarized here, and we've actually kind of evolved a bit since the Cadence note, and I'll discuss that in a bit. So in the kind of baseline, there's 5 fields. We would really like that 5th field to be the Euclid Southern Deep Field. We would like longer seasons than kind of what's typically in the baseline. We want this 2 to 3 day cadence per filter for 4 of the 5 fields. And then this is one thing I'll talk a lot about today, which is a very fast kind of 1 day cadence that is up in like for Cosmos, that's up when other fields are not up. And one thing that kind of we've done a lot of work on just lately is this idea of rolling deep drilling fields, and I'll talk more about that. We have been working on kind of this ramp up of more time for redder filters, because our biggest thing that we need to make happy is supernovae, and as you go to higher redshift, everything gets redder, so it doesn't make much sense to just kind of have equal exposure times for GRIZ. And this seems, I think, is agreed upon with the AGN, which is kind of decoupled filter allocation for U-band. So now let me kind of break these down. Okay, so in the baseline, there's been these kind of 4 decided plus one deep field. So we very strongly want this to be the Euclid field. So this is near Akari deep field south. So sometimes we call it Euclid, sometimes we call it Akari, but it's not exactly Akari. For us, this is extremely critical because that will provide near infrared observations, and we really want this to be synchronous with when we're doing observations, if possible. So if we care about supernovae, we want to make sure that these go off and disappear. So we want to make sure that when Euclid is looking there, then we are looking there at the same time. And then there's another wrinkle of this, which is that there's the Roman survey, which will have its own deep fields, and they are technically not allowed to decide on their deep fields yet. I think maybe not even for a few years. But it's looking like, if I had to bet, I'd say that the Roman fields will be a Roman southern field will be where the Euclid southern field is, but it's not a guarantee. It has to do with like the continuous viewing zone of Roman. But so what we put down into our recommendations is that when Roman is also up, we want to be observing its deep field. And Euclid, I think, I don't know, people are, maybe someone here knows better, but I think the last I heard is like 2020 late 2023, maybe 2024. Roman, I think, won't be doing the supernova deep field observations till like 2028. So when we in our proposed program, we tried kind of hitting Euclid when it was up, and then going back to that field if it's the same, or whatever, going to the Roman field when that was back up, and that like is something we care extremely strongly about. But you could also just kind of see here in one of the problems with the deep fields, which is that you have cosmos separated, but then kind of in terms of RA, you have really the grouping of the four fields, and that is just a difficulty in any DDF strategy, that they're not well spread across the sky. And I think kind of more work needs to be given to figuring out the best way to deal with that. Okay. Okay. So this is a giant table, and sorry about the numbers, but this is kind of what we all deal with, of the different strategies that the project has so far come up with. And just a couple to kind of point out that I've spent a little time on here is kind of what the AGN group has asked for, and then what DESC has asked for, and then kind of another just put your eye on is the baseline. Yeah, I'm gonna just sit on this slide for a little while because there's a bunch of things to say. So the first I should note is that, so when DESC was evaluating the different DDF strategies, we didn't get past version 1.5, and kind of shortly before the notes were due, the project came out with updated to 1.7, which actually had a very big impact. They fixed some issues with the rolling strategies. So kind of from our perspective, the rolling strategies didn't look very good, but now they're actually looking good now that we've started to analyze 1.7. So I'm not sure where kind of the AGN group is with this, but that was a big change. The kind of second big note I'll talk about more later is that there's this question that's going on in the SCOC of should the deep drill, how much of the deep drilling field budget be thought of kind of as baseline, like this is just in our nominal survey, versus if, let's say, LSST is doing really well and for some reason things are just above spec and it has this extra time, then kind of more of that time could be given to different programs, one of which is DDFs. So one thing that I've been pushing for is to try to make sure that the baseline has everything that DESC and AGN would need, and not to rely on this kind of extra component. But this is definitely something that's still being kicked around right now. Okay, so then looking more at, if you just kind of go back and forth between the AGN and the DESC DDF, you could see that the cadence that being asked for is kind of similar. U-band is not really asked for so much. We had this program where we tried to push our visits. I don't know if you can see my clicker. Hopefully you can. But we tried ramping up significantly in the red end, whereas AGN maybe just a little bit. Kind of this is GRIZY. You can see in the top row. Then in terms of season length, the AGN, so it depends on the filter, but it's kind of similar. Maybe the AGN asks for a bit more. In terms of area, very similar. And really the kind of biggest difference is the budget here. And if you look then at the daily DDF, what's kind of right in the middle here, this is not too different from the AGN, but they're just kind of a bigger budget, and it's been a little unclear to me, given that the daily DDF and the AGN DDF have similar cadence. There's a the visits have less exposures, and the season length is the same, how the DD budget is that much more compared to AGN DDF. And you can see this 5.5 to 3.4. But somehow this is happening. So for us, what we see is basically we really strongly don't like the AGN DDF. So I all apologies, but it's not as obvious of why that is. What we actually see is that the daily DDF is better for us than our own proposed DESC DDF. These dither ones are all not very good. And we love the what's called DDF heavy, this one that's 13.4% of the budget. And basically what we like and don't like totally scales with the budget column. That's what we found. And something in kind of how these are being coded up, and what more budget is getting you, and that's what we like. So really, as far as I can tell, the only reason we don't like AGN DDF is because the amount that you all are asking for is so little, rather than it being obvious about what's wrong in the cadence, number of visits, or season length. So and I'll say kind of the number for a budget of 5% has typically been kicked around. So right now, I think AGN is going kind of well under that. And yeah, I'm curious to hear from you if you need to, or you're just happy to scale that up.
And I mean, this may be better for questions, but I don't think we've considered that at all. And probably nobody will complain if there's more time on DDFs. I don't know if Niel wants to comment here.
Absolutely. If they're willing to give us more, that's great. We were conservative in what we asked for, thinking that, we might even suffer further cuts beyond this. But sure,
yeah,
if you want to just take the elements of what we have and add even more, works for me.
Okay,
Sounds
that's already great to hear.
Yeah, go ahead though. Go ahead and finish your talk.
Okay.
Yeah, because I think that from conversations within the SCOC, I think everyone's going to get cut a little bit. So better to ask for more and then get cut down a little bit. It just seems like a better strategy. But a 5% number seems very that is kind of, I think, the more assumed number right now. And I mean, even we went under that because we were also kind of scared. But I don't think we should all be so scared. Okay, so this is just one idea that you all have asked about that we did not consider, this idea of these accordion cadences. So I actually think we will really like this idea. So basically it's trying to address the fact that longer seasons are good, but you don't need the as high cadence near the kind of the edges of your seasons as you do kind of in the middle. And we would, for supernovae, we would totally agree with this. So I don't think we've seen any simulation with that. So we're kind of waiting to see that. But that is an idea that we would definitely support. So that makes a lot of sense, because for supernovae, we need long light curves. Long light curves means you don't want to be cut by edge effects. Okay. Now, one thing that was a kind of surprising to me is we put in that you want, let's say, cadence of every 2 days, but in reality, you have bad weather and just engineering downtime or whatever it is. So this is a plot. This is in Philippe's upcoming paper, just looking at some of these different strategies and showing how kind of for different cadences of the strategies, how it relates to the maximum internight gap between observations. And basically the takeaway point from this plot, for me at least, is that if you don't ask for kind of really good cadence, then you are going to have these big gaps just due to weather. So if you're saying I want every 2 days, you're not actually going to get every 2 days. You will have these big gaps. So better to ask for more, knowing that you're going to get hit by weather and downtime, or else these pretty nasty gaps will be coming. And
you have 3 minutes left.
3 minutes?
Yeah.
Okay. Yeah. Okay. Let me rush then. Okay. Okay. So then the other idea that we've gotten really excited about is this idea of rolling deep fields. So so we basically are not finding a way to get season length, exposure time, number of visits for 5 fields every year. We've looked a lot at it, and it just doesn't seem possible. So what we've started getting excited about is, okay, instead of 5 fields every year, do 2 fields and rotate those 2 fields through. So this is just showing season length and number of visits from a 5% appropriation to 15%. And basically, if you do 2, you really are able to have a lot more visits in season length compared to 5. So we propose 3 different ways of doing this, basically kind of knowing that the AGN group wanted certain things. So we have this, and there's the 5 fields, same depth. Then there's 5 fields where you have an ultra deep and deep fields, and then this kind of 5 where you have these 5 fields where you're rolling, and then the AGN group, if you really don't like this idea, then you just kind of have this you'll have kind of some baseline where you're asking for a little, and then we're going deep on the rest. So that this was kind of me thinking how to make everyone happy. So on the right here, you're seeing kind of what this would look like visually. Let's quickly say that I don't know if the AGN group thought about this, but we basically don't really like dithers. Bigger dithers means a lost area. And then, yeah, let me just kind of talk about the path forward, and I'll end here. So there's going to be a write-up from the SCA coming, where it synthesizes the various cadence notes. I think the biggest discussion for the DDFs is what should the budget be? Because how the project is now coding it up is essentially that DDFs is like a separated thing. And they're even, like, Peter Okim is even writing it so that we, the community, can code up our own strategies. So it's really kind of like a tearaway part, for lack of a better phrase. But what that really means is that if DESC and AGN could agree, we could essentially code it up ourselves and say, hey, this is a strategy that we agree on, and we would like this to be the case. And I really think that has an amazing chance of being reality. And kind of one big kind of ask I have of you all is about this rolling idea, and is there something in this avenue we can make work? Okay, so I'll stop there. So thanks for this opportunity.
Thank you very much. So I open up the lecture for discussion. We have 5 minutes only. So there is also the question on the chat. So Niel.
Hi, Dan. Thanks a lot. This was very helpful. And I think we do agree on a lot. We agree on the basic field choice. We both want a big investment in the deep drilling fields. The only reason why we pushed the accordion was because of the significant loss in total achieved depth for the deep drilling fields. One could be concerned that the deep drilling fields weren't actually going to be all that deep.
Yeah.
They were primarily going to be time domain fields, in which case you almost want to rename them time domain fields. Yep. That's the reason why we put forward the accordion. So I guess my question to you is, did you have any real pushback in the dark energy science collaboration about the deep drilling fields not being super duper deep, not achieving the depths they could in principle?
Right.
We did not. So what was your experience? I was surprised. All the momentum, at least all the people in my ear, were all the time domain people. What is your experience?
Right. So we felt like the deep fields are just not deep enough. And so, I mean, what looks good for us is essentially DDF heavy, but it's taking up 13% of the budget. But that's really, you're going really deep. So, so our solution of being, I don't know, bummed out that the deep fields were not deep enough is this rolling idea. So you could basically go deeper, because we don't care about cumulative over 10-year depth. We care about season depth, and that's that's what the rolling gets us. Because we're just not close to deep enough per year.
So nobody in DESC is really complaining strongly about the integrated final 10-year depth that will be achieved in the deep drilling fields.
No, I think the biggest constraint for us is photoz's, and I think that will be good enough.
Okay, I have a lot more, but let's let other people give their point.
Okay, Maurizio, I think you asked to.
No, go ahead. There are more important.
Okay, Gordon.
So I'll post stuff on the chat, Dan. But I just wanted to encourage. I don't know how much of the meeting you can attend. I don't know that the next couple hours are useful to you, but certainly the discussion would be great to keep these things going at like 1:45, right? But I'll post other things on the chat to sort of guide discussion, I guess.
Sebastian.
Yes. Okay. So thanks then for the overview and the input from DESC. So with regards to this rolling deep drilling fields, I've made a comment in chat already. I mean, one of the problems is that there are science cases at least in AGN that really require essentially an annual kind of every season coverage in the deep drilling fields for as long as possible, right? With as little gaps as possible. I'm thinking about direct photometric reverberation or support of reverberation of spectroscopic reverberation mapping, where essentially having kind of long, gaps of several years could essentially kill the complete science, right? So I think this is one of the parts why, at least I personally, but I can imagine some others here in this group are not big fans of that.
Right. Okay. Yeah. So this is what I thought when we were writing our thing that we said. I'm just having a little trouble. Here we go. So I tried putting in this idea of some kind of where we had, since you all have asked for what I think are kind of a little budget, then we do kind of your thing. We do basically that if that makes you happy, and then our rolling is like on top of that. I mean, that might be the path forward where we can agree, because there's still a good amount of budget left. If you're only kind of asking for this 3%. So
I think this could this could be doable.
Okay, thank you, Roberto. We have only 1 minute.
Okay, very short. So one comment that perhaps is more for the discussion session, but I think for AGN actually, or one of the things that may be difficult is that we do care a lot about the U-band. And actually, it might be good to discuss how that could be compatible with DSC. And then the other thing is just I think a simple question: how does the rolling cadence work with the requirement of observing the Euclid DDFs at the same time as Euclid every time?
Right. So for the latter question, so Euclid will only have like 2-ish years where their survey will be going for the deep field. So for rolling, kind of we're on these 2-year cycles. For the U-band, I guess my question back to you is, can it be decoupled? We care about U-band for photoz's. We just don't care about it for time domain. So do you need to have U-band along with your other filters or not?
So the more decoupled.
Thank you.
Okay, sorry.
I think that we should continue in discussion session at the end of the day. So I will move to next lecture. Fan Zhou from Penn State University. Fan, could you share the presentation with us?
Thank you.
Also, there are several questions at the chat, so you can see and answer. Okay.
I see the screen. Okay. Yeah, I'm going to start, and I'm Fan Zhou from Penn State, and here I'm going to talk about our recent efforts on force photometry, photometric redshifts, and spectral energy distributions in the LSST Deep Drilling Fields. And for this, like for force photometry, I'm referring to multiband force photometry based on other surveys. And as we know that the LSST Deep Drilling Fields, LSST will observe them with greater depth and high cadence. And one of the most important advantages of these fields is that they have rich multi-wavelength data. And here I'm showing the footprints of the multi-wavelength coverage in the WCDFS field. For example, from a shorter wavelength to longer wavelengths, we have X-ray from XMM surfs, and also UV optical and infrared from near infrared to far infrared like Herschel, and also radio data. So the point is that all of these fields, including WCDFS, already have rich multi-wavelength data. And our first goal is to improve the existing photometry and to improve the utilities. And we are only focusing on the ELISS1, WCDFS, and XMMLSS field, and because these fields, I mean, we can improve more within these fields. And the first work is about the force photometry. And before we actually define what the method to measure the force photometry, I would like to briefly talk about one of the most important advantages. The photometric redshifts based on multiband force photometry are better. And here, for example, here I'm showing the comparison between the photometric redshifts versus the spectroscopic redshifts, and derived from the original single band catalogs versus the forced photometry. So we can see that after using the forced photometry, the photometric redshifts can improve greatly. So this is one of the most important reasons driving us to do our forced photometry measurements. And here, let's see how we measure the multiband forced photometry. We are using the code called the Traktor to do the measurements. And the first step is to choose the fiducial band. For example, in this case, there is we are using the video KS band as the fiducial band. And we have 4 detected sources within this small cutout image. And then we obtain the positions and the intrinsic surface brightness profile of all of these 4 sources. And of course, we need to convolve the profiles with the point spread functions at this band to get the model. And if we want to obtain the photometry at another band, let's say if you want to measure the photometry at 4.5 micron, then we just fix the position of all of these 4 sources, and also its intrinsic surface brightness profiles, and convolve the profiles with the point spread function at 4.5 microns. And we only allow the fluxes of these 4 sources to vary freely, and the best fit, we use this method to fit the image, and the best fit fluxes will be the so-called forced photometry. And we can see that during this process, the low resolution images can be deblended automatically. That means, for example, in this case, it's very hard to know whether this is 1 source or 2 sources only based on the 4.5 micron image. But with a fiducial video image, we already know that there are 2 sources, and we can fit both of them, so we can deblend the low resolution image. So this is another important advantage for the forced photometry. And also here I'm summarizing some of the advantages for the forced photometry. And as we said, we can improve the photometric redshift, we can deblend low resolution images, and we can also provide consistent source cross identifications among bands. For this, I'm meaning that normally when we want to construct a multiband photometry catalog, then we need to cross-match different catalogs from different bands. But with the force photometry technique, we can all of the sources are automatically cross-matched among different bands. And the last thing is that the force photometry can provide higher source detection fractions, and I will show that in the next slide. And in this figure, I'm showing the results. Here I'm showing the results in LSS1 field as an example. We provide the force photometry for all of the sources in the LSS1 field in 16 bands from the U band to 4.5 microns. And this compares, as an example, I'm comparing the video Z band magnitude, the first video Z band magnitude versus the original video Z band magnitude, and they generally agree well. And in this panel, I'm showing the histograms of the 4.5 micron magnitude for the original photometry, original catalog, and our first catalog. And we can see that we are able to push the detection limit to a fainter magnitude regime. And here I'm cutting out at a 2 sigma level. So that means we are able to provide more information for faint sources with the force photometry technique. And this is for LSS1 and the force photometry catalogs in the WCDFS, and also the 4 XMMLSS field will also be released soon by Christina Nyland. And with the improved force photometry, we are going to derive a better photometric redshifts for all of the sources within these fields. And this is necessary for the deep drilling fields because the spectroscopic redshifts are very expensive and very limited. For example, less than 4% of sources within these fields have spectroscopic redshift measurements. So we will need to rely on the photometric redshifts for most of the sources. And we are using the template fitting technique, and we're using this code, and it will fits the SEDs, the spectral energy distributions, with a linear combination of 9 templates. And here I'm showing these templates, and we allow the redshift to vary freely, and the resulting best fit redshift is just the so-called photometric redshifts. And the results are here, and this work is mainly done by Guangyang. And here I'm showing the photometric redshift versus the spectroscopic redshift in the WCDFS and also LSS1. And the upper left panel shows some statistics, including the normalized median absolute deviation, and also outlier fraction defined by these 2 equations. And especially we define a parameter called QZ to quantify the quality of the photometric redshift measurements. And this is independent from the spectroscopic redshift. And here I'm showing, for example, for the high quality photometric redshifts plotted as these blue points, they are generally confined within this outlier boundary. But for the low quality photometric redshift plotted as these red points, they are more scattered. So that indicates that this this is an empirical parameter, but it can be a good indicator for the reliability of the photometric redshift. And also, I would like to note that the photometric redshift catalog in the XMMLSS field has already been published in Chen et al. 2018, which is a paper releasing part of the X-ray point source catalogs in the XMM field survey. And here, so the previous figure only compared the photometric redshifts for those sources with spectroscopic redshift measurements, but for the remaining majority of sources, we are not able to know the actual spectroscopic redshift, so we rely on the QZ parameter to quantify the reliability. And here I'm showing the probability that a source has a high quality photometric redshift measurements as a function of the I-band magnitude, and we can just look at one line, and we can see that when the I-band magnitude goes above about 24, the fraction of high quality photometric redshifts will drop drastically. So we conclude that nominal depths of our high quality photometric redshift measurements is about I-band magnitude equals to 24. And I would like to briefly talk about one problem. So our adopted templates are only for pure galaxies. So that means we didn't remove like stars and also AGNs from our analysis. So first for stars, of course the redshifts are 0, and and different users may want to apply their own criteria. So we just leave this work to the users. And for AGNs, I would say that even if a source is an AGN, it doesn't necessarily mean that the photometric redshifts based on the pure galaxy templates cannot be is not appropriate for these AGNs. I mean, only those AGNs that are strong enough to significantly change the optical to near infrared spectral energy distributions can have problem. So, and these AGNs are mainly broadline AGNs, and I would like to refer you to Qinglini's talk for more details about the photometric redshifts for AGNs, and she will be the next presenter. And here, I would like to briefly talk about the spectral energy distributions, and this work is still ongoing. So we haven't had organized results. So I would like to mention our goals and plans. So we are working on analyzing the spectral energy distributions from X-ray to far infrared with the code called X-scale for all of the sources in these 3 fields. And here I'm showing the one of the example decomposing the spectral energy distributions. I would like to highlight something. So first, we have X-ray data from the XMM survey, and for those undetected sources, we will also provide upper limits to constrain the AGN power, and also we will add AGN emission, and eventually we will also add far infrared, which is not shown here. And during this process, we can constrain both the AGN and the galaxy emission and the physical properties. And the goals, we have several goals. The first goal is to select AGN candidates missed by other AGN selection methods such as X-ray or mid-infrared. And also we will constrain the AGN contribution for these AGN candidates, because we will add AGN emissions in our SED feeding process. And also the second goal is to obtain the galaxy properties for all of the sources, including AGN host galaxies. And especially we want to obtain the stellar mass and star formation rate for the host galaxies. So this will allow us to probe the coevolution between the AGNs and the host galaxies. And the third goal is sort of a byproduct of our work is to deblend Herschel far infrared images. So I mean, we know that the Herschel deep images within these fields are usually highly deblended and nearly confusion limited. So, but the far infrared fluxes will be very important to constrain the star formation rate. So we are also working on deblend the Herschel far infrared images within all of these three fields. And this is our three goals. And
you have 3 minutes left.
Okay, yeah. And here I would like to summarize our my presentation. So as we said, we have multiband force photometry catalogs in all of these three fields, at least for ELISIS-1, but the catalogs will be available for these two fields as well in the future, in the near future. And also we provide photometric redshifts with the improved improved force photometry. And we are conducting a comprehensive analysis of the spectral energy distribution for all of the sources, including both galaxies and including both galaxies and AGNs, and with our improved force photometry and also photometric redshifts. And hopefully this work will prepare for the future science in these LSST deep drilling fields. And I will stay here for any questions. Thank you.
Thank you, Fen. So I open the talk for questions. Magda, please.
Thanks for this really nice talk. I was just wondering, in terms of your plans for LSST, so you talked about the forced photometry using Traktor.
Yeah.
Have you, could you comment on the kind of computational requirements for running Traktor on the LSST deep drilling fields? Is your plan to take the LSST images and run Traktor on the images? How is that going to kind of connect with the LSST stack outputs? Do you have any kind of thoughts on that?
Yeah. So for the computational question, it will take 2 weeks to do a single run for one single field. So the computational requirements are quite heavy. And for the LSST, I think they will provide their own single band their own force photometry on the single exposure image. And for the collated ones, I would say we have to wait until they actually release their data. So we are currently not planning to write a pipeline to deal with all of the LSST images.
Right. So just to understand, so you're proposing doing the Traktor just for the infrared and then combining that with the LSST DM.
Yeah. From U band down to the infrared. That's the so we are using the Traktor to do a multi-wavelength catalog for all of the related surveys.
Okay, so when LSST data comes along, you would propose running Traktor on the LSST images as well?
Yeah, that's one possible plan, and we haven't thought about that deeply.
Okay, thank you.
Thank you. Mike Strauss?
Yes, thank you for a very interesting talk. Can you go back to the first slide where you're showing the Traktor results, showing, the images there? I was intrigued by the chi-squared values that are quoted there. The first one has a chi-squared per degree of freedom much less than 1, which suggests the errors are not right, and the others have values quite a bit larger than 1. I wonder if you can comment.
Yes, so this chi-square value, first it depends on the brightness of these sources. So bright sources will have larger chi-square, and is just an indicator for a single band. I mean, for a single band, the lower chi-square value indicates the fits are better, but it's hard to compare the chi-square value across bands.
Yeah. So perhaps the errors in the first image are overestimated, or there's, given that chi-square of 0.1 suggests that there's something systematically too large about the errors, or something like that.
Yeah. We are not relying on the chi-square to derive the errors.
Yes.
Instead, yeah, we are using the background fluctuations.
Yeah. And I wonder if I can ask a follow-up question, if there's time, which is the debate that we were having earlier about the need to go really deep in the coads. I wonder if you have an opinion on this, based on this, whether the full coadded depth is the most important thing for the deep drilling fields, as opposed to the time domain aspects, which we were also discussing.
That's an interesting question. I would say the U, obviously for the U band, the depth will be important, but for the GRIZ band, well, so currently I don't have a clear idea on that.
Yeah, certainly something for us to discuss in the discussion section.
Yeah.
Yes, absolutely. Thank you.
More questions? One you have also chat concerning what one paper you can see. So if not, we will move to next lecture. Xin-Ling Ni, also from Penn State, will talk about XMM SERS, sensitive X-ray survey of the LSST deep drilling fields. Please.
Oh, I just realized I was muted before, so hope everybody could hear me well now.
Yes.
I'm Xin-Ling Ni.
Yeah, we can hear you.
Thank you. I just graduated from Penn State. I was working with Niel, and today I'm very glad to present a completed observations of a sensitive X-ray survey of much of the LSST deep drilling field XM SERS. The XM SERS survey is a large long-term project, and the XM SERS collaboration is a large international team of about 35 people. Here I show the X-ray images of two of our fields, WCDFS and ELIASS-1. The apparent size of the full moon is shown to scale in both of these images. These two images are from a recent paper of our XM SERS collaboration that has been accepted by APJS that focuses on the X-ray source detection and characterization in WCDFS and ELIASS-1, which makes up the main content I'm going to talk about today. And some of our collaborators among the audience, I think I see at least Guang, Fan, Franz, Mark, Mara, Dang Yongchen, and Dr. Amanda Bernard, Dr. James Mulani, Mauricio O'Hart, and Mo Yuan here. And thank you for all the great contributions you made. So these two fields, WCDFS and ELIASS-1, combined with an earlier field, XM and LSS, that our team published in 2018, make up the whole XM SERS survey that was conducted with the XM Newton X-ray Observatory. The XM SERS survey helps to fill the gap between deep pencil beam surveys and shallow wide field X-ray surveys, which are two popular types of X-ray surveys. Deep pencil beam surveys, as you can see from its name, are deep X-ray surveys in a small area. They could detect low luminosity AGNs. However, they do not have the contiguous volume needed to explore AGN activity over a wide dynamic range of cosmic environments and to sample substantially the high luminosity tail of the AGN population. At the same time, shallow X-ray surveys over large areas have made excellent progress sampling the luminous AGN populations and their environments, while they lack the sensitivity to detect the bulk of the supermassive black hole growth. To fill the gap, we have surveyed 3 Spitzer extragalactic representative volume survey fields with 5 million seconds of XM Newton observations, and this is where the name XM serves come from, which is sufficiently sensitive to capture most of the cosmic black hole accretion power while also covering respectable areas. Also, as you know, all the XM survey fields are LSST Deep Drilling Fields. X-ray data will wonderfully complement LSST data for studies of AGNs as well as other cosmic sources. So in the WCDFS fields, we have conducted 80 successful new observations with a total exposure of 2.3 million seconds. And in ELISAS-1, we have 31 successful new observations with total exposure of around 1 million seconds. Due to the potential background flares, our observing strategy adopts a 2-round approach. We first observe all the design pointings and check whether there are some observations that are severely affected by flares. If so, we just re-observe the affected areas for a second time in order to reach a rather uniform exposure. So 1.8 million seconds exposure remains after flare filtering in WCDFS, and 0.9 million seconds exposure remains after flare filtering in ELISAS-1. Here, I also show the cumulative survey solid angle as a function of 4-band effective exposure in WCDFS and ELISAS-1. The median PM plus most exposure across WCDFS is 84 kiloseconds, and this number is 80 kiloseconds for ELISAS-1. Due to our observing strategy, we achieve a rather uniform sensitivity across our wide survey fields, as can be seen in relatively smooth sensitivity maps here. I also present the sensitivity curves for the 2 fields. Basically, the sensitivity is similar for WCDFS and ELISAS-1. The survey in WCDFS has a flux limit of around 10 to the minus 14 erg per centimeter square per second in the 0.5 to 10 keV band over 90% of its area. And this number is 1.3 times 10 to the minus 14 for ELISAS-1. So with our obtained XM Newton data, we could detect accurate sources, including AGNs and clusters. Here I show an X-ray cutout in WCDFS. As you can see in this cutout, most of them are point-light accurate sources, such as the source inside the yellow circle here. And these point-light sources are mostly AGN that we are interested. There are also a small fraction of extended X-ray sources detected, such as the one within this white circle, where X-ray emission comes from hot gas in a galaxy cluster. Our work focuses on the detection and characterization of point-light sources since we're interested in studying AGNs. We first perform a first-part source detection for each individual observation and use the obtained source list to perform astrometry corrections for each single observation. Then we combine all the individual observations together into a single mosaic image where we perform a second-part source detection, which gives us the final source list. Particularly, unlike previous work, we adopted a new 5-band detection approach, which has greatly improved the positional accuracy of sources detected. Astrometry accuracy is very important, since finally we need to match our detected accurate sources to their multi-wavelength counterparts in order to construct the 4 SED to characterize these sources and link them with LSST data in the future. The larger the positional uncertainty, the more likely a wrong counterpart will be matched to the accurate sources. So in our approach, we create images in 5 narrow X-ray bands separately and run the source detection based on the likelihood provided separately by these bands. The median positional uncertainty of X-ray sources detected is around 1.2 arcsecond. This is very impressive. For the first XM served fields, the background level is smaller, but the median sigma x is still around 1.4 arcseconds. So in total, around 4,050 3-point sources are detected in WCDFS, and 2,630 point sources are detected in ELISAS-1. Here I also show the counts and flux distributions of these detected sources to give a basic view of the properties of these X-ray sources. So with the X-ray source list obtained, we start to match X-ray sources to their multi-wavelength counterparts. As you have already known from Fan's talk, all the XM source fields have superb multi-wavelength data coverage. In the infrared, we have the combination of deep drill plus serves that gives deep infrared coverage at 3.6 and 4.5 5 microns. And there are also video survey provide deep CYJH KS band coverage. And for WCDFS, we have HSC and voice in optical. For LSS1, we currently use dark energy survey and ESIS survey in the optical. Also in the video survey region, we have the wonderful force photometry catalogs, which gives us flux measurements in all the bands consistently, which greatly aid the characterization of sources. So while we have used various techniques when performing the accurate source detection to improve the astrometry in accuracy, however, the sources, the XM Newton source, the positional uncertainties of XM Newton sources detected are still larger when compared to Chandra sources due to the instrumental nature. So we use N-way to identify counterparts for our detected XM Newton sources, utilizing priors obtained from Chandra sources that are matched to our detected XM Newton sources. We tested various sets of prior combination and chose a prior set that gives the smallest false positive fraction at a given completeness, which is basically the source position on the IREC1 minus IREC2 color versus IREC1 plus IREC2 magnitude plane, and the KS band magnitude and the I band magnitude. So with this prior set, around 89% of the accurate sources in WCDFS have reliable multi-wavelength counterparts, and this number is 87% for sources in LSS1. Here, reliable means a false rate of around 5% according to our simulations. Here, I also show the X-ray to optical positional offsets of sources in WCDFS with contours in circles 68% to 95% of the sources. We could see that nearly 70% of the accurate sources have its multi-wavelength counterparts within 2 arcseconds. Here I also show some HSC color images of the counterparts of the accurate point sources detected, which are mostly AGNs. You can see in some cases their host galaxy dominates in the optical, and in some cases not. With these reliable multi-wavelength counterparts identified, we would like to derive photosets for the X-ray sources, as only 1/4 of the sources have spectroscopy redshift, and redshift information is important for characterizing these sources. Since the optical to near-infrared SED of broadline AGNs roughly follows a featureless power law, deriving their photoset is relatively difficult, and special techniques have been developed. Thus, before performing photoset measurements, we want to identify broadline AGNs among accurate sources detected. We identify broadline AGNs through SEDs by 2 different methods. One method is machine learning. Basically, we train the convolutional neural network to study the observed frame SEDs of broadline AGNs and non-broadline AGNs that have spectroscopic classification available, and then let it predict the class for sources without spectroscopic classification. Another method we adopt is axial template fitting, where we perform optical to X-ray SED fitting to identify broadline AGNs directly, and no training is needed. These 2 methods have their own advantages and disadvantages. As you can see from the confusion matrix shown here, the machine learning method could achieve a higher apparent level of accuracy. At the same time, since this method is established on training based on the sources that have spectroscopic classification available, there might be potential bias associated with this process, since sources that have spectroscopic classification are relatively bright. At the same time, while the apparent level of accuracy of the axial template fitting method is not as high as the machine learning method, the accuracy is still good and it does not suffer from the potential bias. In the middle of the slides, I show the Venn diagrams for broadline AGNs identified via the machine learning based approach and the axial template fitting approach. So if a source is identified as a broadline AGN by both of these methods, we think this source is very likely to be a broadline AGN. So for non-broadline AGNs, photosets are derived utilizing the default galaxy templates in EASY as introduced in Fan's talk. We assess the quality of these photosets measurements among sources that also have SPECSY available. Here I show the histograms of the fractional differences between the easy photosys and the SPECSYs. The outlier fractions is typically around 5% to 7%, and the normalized median absolute deviation is around 0.303 to 0.04. For broadline AGNs, photosys are derived utilizing the SED library designed for fitting AGN-dominated sources in LaFair, and magnitude priors are also adopted, and Galactic Photometry are also adopted when available. Similarly, we use sources that also have SPECSY measurements to assess the photosy quality. The outlier fraction is around 17% to 20%, and the sigma NMAD is around 0.06 to 0.07. These numbers are relatively larger compared to those of non-broadline AGNs, but they're still good considering that the photosys of broadline AGNs are relatively hard to measure. So in the plots shown here, the cumulative distributions of the I-band magnitudes for sources with either high-quality photosys or SPECSYs are shown as a green curve. And the sources that only have SPECSY available are shown represented by the blue curve, and all accurate sources that have forced photometry measurements available are shown as a gray dotted curve. You can see from this plot that our photosy measurements largely increase the number of sources that have redshift information available. So in total, around 84% of sources in WCDFS and ELISA-1 with forced photometry available have either SPECSY or high quality photosy measurements. Here I show the distributions of the redshift of accurate sources that have either SPECSY or high quality photosy. You can see that our sample spans most of the cosmic history well. So with all this information, we classify around 3,186 sources in WCDFS and 1,985 sources in ELISA-1 as AGN, mainly based on the following criterion. First, if the source is identified as an AGN in spectroscopic survey, it is clearly an AGN. Secondly, if a source has observed X-ray luminosity at rest frame 2 to 10 keV greater than 3 times 10 to the 42 erg per second when the source has redshift information available, we classify the source as an AGN. Third, if the source has a power law effective photo index smaller than 1, we classify it as an AGN. This criterion helps select hard accurate sources that are heavily obscured, which are likely AGNs rather than X-ray binary populations. Fourth, AGN identified in X-Gale template fitting introduced earlier are directly adopted. AGN selected via this SED-based selection methods already include AGN selected from empirical methods that use large X-ray to optical or X-ray to near infrared flux ratios. We know that these 4 methods could already effectively identify most of the AGNs among accurate sources. In case there are missed AGNs, mid-infrared color selection are also utilized when available. Accurate sources that are only identified as an AGN via mid-infrared colors are marked by orange stars in this classic mid-infrared plot. So basically, the mid-infrared AGN selection method only adds tens of AGNs to our final catalog. And similarly, if we use radio properties of accurate sources as well to perform radio AGN selection among accurate sources, the number of new AGNs identified is also very limited.
You have 3 minutes left.
Thanks. The completion of the XM Newton observations in the WCDFS and ELISA-1 fields marked the end of the XM survey data gathering. For the 3 XM survey fields together, we detect around 11,900 extra point sources together, including around 10,200 AGNs and about 2,800 of them are type 1 AGNs. There are also around 1,000 galaxies and hundreds of stars detected. The point source sky density of the XM surveys is around 910 per square degree, which is larger compared to that of E Rosetta, and XM Newton precisions are considerably better. Also, due to the superb multi-wavelength data coverage of XM surveys, the overall number of detected accurate sources with reliable redshift measurements is large at all redshifts, as can be seen in the upper panel of this plot, which shows the redshift distributions of sources from several selected deep pencil beam surveys and shallow X-ray surveys over wide areas, together with XM surves represented by the gray histograms. Also, from the X-ray luminosity distributions in the right panel, we could see that compared to shallower surveys over wider area, the XM surve surveys could detect a significantly larger number of moderate luminosity AGNs at around log LX around 42 to 44. So the AGN sample provided by XM surves will benefit large sample studies of supermassive black hole growth and AGN properties in the future. And particularly, AGNs identified by XM surves could serve as a ground truth sample of AGNs to calibrate the AGN selection algorithms in deep drilling fields. One of the XM surve fields, XMM LSS, already contributes to the LSSTC AGN data challenge. The AGN selection algorithm trained in deep drilling fields with a ground truth sample provided by the XM surve survey could be further applied to the main survey, which will ultimately help LSST find tens of millions of AGNs. Also, compared to the AGN sample provided by other X-ray surveys, the AGN sample provided by XM surves will enable us to study supermassive black hole growth across a full range of cosmic environments, which will be unbiased by local cosmic factor. As we could see from this cosmic density field simulated at redshift around 1.4, a single survey field is not able to capture all the cosmic structure, while separate large fields can. And I think most of you know that these survey fields are not only the deep drilling fields of LSST, but also the size of several spectroscopy surveys in the next decade that will provide accurate redshift measurements and characterizations to AGNs, and in some cases, measure the mass of the supermassive black hole. These fields are also the size of other upcoming surveys in the radio, some millimeters, and infrared. As mentioned in several talks this Monday, these multi-wavelength data are very important for studying AGNs and their host galaxies. So I will just leave my summary slide here. And one last point I want to mention is that we have released all the data points, including the X-ray catalogs, images, exposure maps, background maps, and etc. in the website here. And we hope these X-ray data products could be very useful for the LSST and AGN community. Thanks for listening. Thank you.
Thank you, Xingling. So I open the lecture for questions and comments. Amanda, please.
Thanks for another really nice talk. I was wondering, you showed really nicely the X-ray sources that you've then checked how many of those are AGN by, comparing to spectroscopic data sets or mid-infrared data sets. Have you done the opposite exercise where you've taken spectroscopic, say, SDSS quasars and seen how many of those are in your X-ray sample? Are there SDSS quasars that aren't in your X-ray sample? And if so, do you understand why?
That's a really nice question. First, I want to mention that for the XMM LSS, which is our first XM survey field, SDSS spectra available, but you see, due to the location of the WCDFS and ELISS1, these two fields lack the coverage from SDSS. So, so spectroscopy surveys come from OZDES and Primus previously, and I haven't. And the answer to your question is I haven't checked how the reverse, how many AGNs identified in other spectroscopy surveys, mid-infrared surveys, and radio surveys are missed by the actual detection. But our group, including what Fan is doing now, they are doing this type of work, seeing what really checking consistently, showing the Venn diagrams, how these each pictures are kind of merged together. But I haven't checked myself, but there are ongoing works about this.
Okay. I can comment briefly, Amanda.
Sure.
The XMM serves and XMM LSS does very well on the Sloan quasars.
Mhm.
We do miss a couple, and they generally are broad absorption line quasars, typically the low ionization broad absorption line quasars,
Interesting.
which are known
Mhm.
often have quite heavy X-ray absorption. But
Mhm.
we detect most of the broad absorption line quasars, And the ones that you don't detect are the ones we would expect not to detect, the low ionization ones. And this is well understood from studies of Bell quasars, but we're certainly on top of that. It's a very good question.
Thanks, Neil.
Okay, more questions? Also no comments in chat. So now we have a short break, and we will see at noon at 12. So I ask speakers